more in their presentation. So the measuring methods, I told you, we are discussing about a sensor, a potentiostat, a spectrometer, and all this measuring change allows us to determine the presence of biogenic amines. Regarding the sensors, we prepare several new sensors, and also we prepare some sensors having additional working electrodes. Why? To be sure that the selectivity is very well ensured, and to have a validation of this this measuring process. In this stage, we used some voltammetric methods, meaning cyclic voltammetry and also linear sweep voltammetry. It's important to establish a proper measuring domain, and to make these measurements on multiple channels, we have some customized solutions regarding electrochemical measurements on 2 or 3 channels for this kind of electrodes. We are using a customized solution, meaning that we are scanning several working electrodes in the same time, or we use also some existing commercial solutions that are equipped with 4 channels or 16 channels, depending of the situation. Regarding the hardware configuration, of course, here they have a commercial cell equipped for this combined method, but we are also using a customized one. The purpose is to use a customized one and to adapt this customization to be able to measure in the field, because the commercial one is suitable mainly for lab measurements. So in this respect, we have some 3D printed modules that are constituting the cell. So the electrode is mounted in the cell. The cell is closed with magnetic, let's say, contacts, and then we are putting there. In this picture, you have an optical fiber which goes to the spectrometer, but we have also a version of upper cell module that is compatible with the camera, finger camera. The difference between these 2 solutions is related to the quality of the determination, because we have a good spectrometer with fiber optics, and we have a UV-Vis measurement with a very narrow resolution. But also with the camera, we can identify some portions of some areas of the working electrode, and to identify which are the most important wavelengths that are relevant for this measurement. So we are going in this direction to be able to obtain a customized solution to be used in the field. So go outside and to measure, if necessary, the food directly in the interest area. Regarding software, we worked a lot to make the embedded software, because we are using also a customized solution for electrochemical measurement. So there is an embedded software, but also in the instrumentation software include control of the spectrometer, control of the trigger of the spectrometer, and also to be able to communicate these results, if necessary, via Wi-Fi. Why it's important to make this kind of integration, software integration, because when we have voltammetry, we need to take a spectrum every step of the voltage scanning. So let's say every 50 millivolts, we are sending a trigger to the spectrometer, and the spectrometer will take the response, the optical response. So we will combine these measurements, and we will be able to make this measurement more precise. On the right side, it's a comparison. It's an electrochemical measurement. It's a comparison between several functionalization of the electrodes. So there was several approach, and the response of the electrodes depends of the nanomaterials that were used in that functionalization. So we have software and hardware developments, which gives us the possibility to go outside the lab and to validate this solution and these measurements. In conclusion, it's a custom platform which combines two important methods to determine these biogenic amines in food and to prevent some health issues. These activities were sustained by the Ministry of Research, Innovation and Digitalization, and is part of a PhD project called AmiFood. Thank you for your attention, and if there are some questions.
Thank you very much. We have Petru, we have a very long collaboration, I think 15 years already.
Maybe more.
Yes, maybe more. I know that it's difficult for you as an engineering and automatization and to present this kind of chemical aspects. And I'm sure that for this, for the chemical aspects, the next presentation will clarify if there are some questions. But if you have questions regarding the sensing and the automatization part, please. Is someone from the room or from online? If there are some questions. Okay. Oh no, thank you very much again.
Thank you.
And good luck. Thank you. I want now to ask Professor Sârbu to introduce the next presentation.
Thank you. Next presentation is design and development of MIP-based electrochemical sensor for cortisol detection. The communication was realized by Maria Lorena Jinga, Lucian Gabriel Zamfir, Petru Epure, Daniel Preda, Mariana Constantin, Iuliana Răuț, Maria Luisa Jecu, Mihaela Doni, Iulia Gabriela David, and Ana Maria Gurban. Please, Lorena.
Thank you. Hello, my name is Maria Lorena Jinga, and I'm part of Bioanalysis and Biotechnology Department. Our study involved the development of electrochemical tools for cortisol determination, a very important compound in our body functions. Firstly, I will present the importance of cortisol, the study of the voltammetric behavior, and the modification of the different electrode surfaces, and after that, the electropolymerization step on these electrodes. After, I will present the indirect voltammetric determination of cortisol using these modified electrodes, and in the final, I will highlight some conclusions and perspectives. Cortisol is a steroid hormone produced by adrenal glands, and it is involved in a large number of processes. This compound helps us in stressful situations, and it regulates metabolic functions and stimulates gluconeogenesis for brain activity. Moreover, it is a biomarker of stress, being involved in immunosuppression and inflammatory responses. In a first attempt, the electrochemical behavior of this important analyte was studied using pencil graphite electrodes and screen printed electrodes. The electrochemical techniques used were cyclic voltammetry, differential pulse voltammetry, and electrochemical impedance spectroscopy. We also used two supporting electrolytes. For the acid medium, we used acetate buffer, and for the neutral medium, we used the phosphate buffer solution. Cyclic voltammograms were recorded in phosphate buffer solution for different concentrations of cortisol. In the anodic range of potentials, cortisol didn't show any oxidation signal, but the small peak which is revealed is due to the polarization of the electrode. Due to the higher sensitivity in detection, differential pulse voltammetry was used to observe the behavior of this compound on pencil graphite electrodes. As you can see, a higher signal was highlighted for the electrodes in absence of cortisol, and no additional peak appeared in presence of cortisol. So the direct determination of this compound can be possible because cortisol doesn't present any electrocatalytical behavior. Further, we performed the indirect determination of this compound using ferriferrocyanide as redox couple based on the decrease of the oxidation signal. As it can be observed, the decrease of the oxidation the oxidation signal decreased, and the peak potential shifted to more positive values. And this suggests that cortisol binding on the electrode surfaces occurs on the electrode surfaces. And even if the indirect determination was possible, the decrease of the peak signal was quite small. In order to improve the results, we modified the electrodes with polymer films. So the synthesis took place by electropolymerization method in absence and in presence of cortisol by using proflavine as monomer. After the polymerization with proflavine and cortisol, the removal of the compound took place, and the specific cortisol gaps were created in the polymer film. A further incubation in cortisol would fill some of them with the specific molecule. The scanning electron microscopy images show the electrode surfaces without modification and with modification by polymer and polymer containing cortisol. In the first case, for the unmodified electrodes, the rough of the surface was high, and while in the case of the modified electrodes, an uniform distribution of polymer can be observed. The cyclic voltammograms recorded during the electropolymerization of proflavine in absence and presence of cortisol were recorded on pencil graphite electrodes. As you can see, a quasi-reversible redox couple is highlighted by the presence of two peaks. One oxidation peak in the anodic range of potentials at around 0.3 volts, and one reduction peak in the cathodic direction at 0.2 volts. And the fact that these peaks decrease slightly in intensity with increasing number of scans suggests the formation of a conductive polymer film on the surface of the electrode. The shape of the recorded and repeated cyclic voltammograms in the presence of cortisol is similar to that obtained in absence of cortisol, but the background current and signals intensities were higher. And this indicates a change in the structure of polymer due to the incorporation of cortisol into the polyproflavine matrix. The next step was the indirect determination of cortisol by using these modified electrodes using ferrocyanide in presence of cortisol. All measurements were performed in phosphate buffer solution. Fourthly, in the case of using non-imprinted polymer electrodes, the decrease of the signal didn't vary significantly, so these kind of electrodes can be used for this determination. On the other hand, in the case of using molecular imprinted polymer electrodes, the indirect determination was realized without and with extraction of the template in ethanol. So, as you can observe, the peak values were higher for the molecular imprinted polymer electrodes after extraction, and the difference between the first and second peak was 10 times higher, which suggests that this kind of electrodes have shown greater sensitivity. In order to have a comparison, similar studies were done on screen printed electrodes, and from differential pulse voltammograms can be observed that no modification took place in the case of these electrodes. And in the final, for the purpose of checking if there were some problems with the electrons transfer at the surface of the electrode, electrochemical impedance spectroscopy was realized using the ferrocyanide as the redox couple. In conclusion, from this electrochemical study, it was shown that cortisol doesn't have electrochemical activity, but the indirect determination of this compound was realized with success using the redox couple ferrocyanide. On the other hand, the study highlighted the fact that molecular imprinted polymer electrodes have a lot of advantages in using them in detection, and the interest for the development of faster and more sensitive detection methods for clinically analyzed, in this case the cortisol, has increased considerably in last years. The next step for our studies will be the optimization of the parameters of on the screen printed electrodes, because we intend to realize flexible and miniaturized sensors for cortisol determination in sweat. Thank you for your attention, and I acknowledge the financial support through the project ERANET Full Sense. I'd like to express my thanks to all my team and to my teacher from university for help me helping me with the study on pencil graphite electrodes. I'd also like to say a big thank you to Mrs. Doni and Mrs. Ana Maria Gurban for the support and efforts which were proven every time for our team.
Thank you. I would like to know if you have the scanning electron microscopy characterization of the electrode surface before and after the modification with the electropolymerization.
Yes, we have them only for pencil graphite electrodes because for the screen printed electrodes we have to optimize the and we have to realize the scanning electron microscopy images too. In the case of screen printed electrodes, we only started the studies, and it's very important to have a comparison, to have this comparison with the pencil graphite.
Okay. Do you have an idea about the coverage of the surface?
The pencil graphite electrodes are a little bit weak and can be used only one time or maybe two if they can be kept. The screen printed electrodes offer the reproducibility because they have more stability, and it's important to have this kind of electrodes because we intend to use them for the determination for the analytical compounds and to develop a patch for cortisol determination in sweat.
Okay, thank you.
Thank you.
Thank you. Another question?
Congratulations, you are so young and deliver such thorough work, but we have also a team helping you. Excellent presentation. My question, you said that cortisol is not electrochemical active.
Yes.
That wasn't known? You discovered that it's first time that it was?
Yes, the first step in
okay. No, I understand, but if that should be presented. Okay. But if it's okay, I understood. I understood. Maybe to say, no, it's very good that observation from my perspective, but should say it is known and we again measured is not active. We confirm. Yeah. But no conclusion. It's okay.
Yes.
Okay. Congratulations. Excellent work. Very promising. Congratulations. Keep on working, and you have a big team near you. Good. It's big experience. But, thank you.
When we start an electrochemical test, the first step is to determine to have this determination directly, and after that we go to check if we can determine it indirectly or in other ways. And that's why I started the study like this.
Yes, this is the answer. Very good.
Thank you so much.
So, there are other questions? If not, we will pass to the next presentation.
Thank you so much.
Thank you, Lorena. So we pass to another Lorena, is Ana Lorena Neagu, presented a paper with all the group formed with Ana Maria Zaharia, Marinela Victoria Dumitru, Iulia Elena Neblea, Sorin Dolana, Tanța Verona Iordache, Carmen Elena Tebrencu, Rodica Zăvoianu, Octavian Dumitru Pavel, Alina Târșoagă, and Professor Andrei Sârbu. So Lorena will present a paper on oral communication drug release system based on biocompatible hydrogel charged with layered double hydroxide containing encapsulated Rhamnus fragula phytoextract. So please, Lorena.
So nowadays, classical drug delivery system can present some inconvenience, and to overcome this kind of inconvenience, several materials have been developed in time, such as polymeric nanoparticles or inorganic nanoparticles, and so on. Layer double hydroxide are considered to be kind of materials which are good for this type of application due to their capacity to storage the drug inside their interlayer space. Also, a hydrogel is a material which is a water absorbent material based on a polymeric chain with a hydrophilic group with a gel-like aspect. The combination of these two are usually used for this type of application, and thus in this study is presented the intercalation of the layer double hydroxide inside the hydrogel, the layer double hydroxide was previously encapsulated with the Ramus frangula phytoextract, obtaining the encapsulated hydrogels. So the synthesis of the composite hydrogels is based on in situ polymerization in aqueous solution, and with polyethylene glycol diacrylate, and initiated with APS ammonium persulfate aqueous solution, and tetramethyl ethylene diamide. So thus, for this application, the hydrogel was obtained by the ultrasonication of different type of LDH with or without the phytoextract in distilled water for 30 minutes. In the meantime, the APS aqueous solution was prepared. Meanwhile, the necessary quantity of PEGDA, TIMEDA, and distilled water was inserted in vials, glass vials. And after the ultrasonication time, the mixture of LDH was added onto the mixture of PEGDA, TIMEDA, and was subjected to homogenization for 2 minutes under magnetic stirring at 400 RPMs. After that, the APS solution was added and was subjected also to homogenization for other 2 minutes under nitrogen treatment. Then the vials were sealed and they were stored at 37 Celsius degrees for 24 hours. At the end of the reaction time, the vials were broken, the hydrogels were recovered, and they were cut into small discs. For the purification step, this disc was put in excess distilled water for 7 days, and the water was changed every day in order to remove the unreacted products. And after the purification, the swollen pieces were dried at 400 Celsius degrees, at 40 Celsius degrees, sorry, until they reach a constant value and they become aerogel. So as results, the FTIR results present that the LDH spectra, in the LDH spectra, we can find the characteristic peaks of the stretching vibration of OH and iron-oxygen bonds. Also, we can find some different bands depending on the type of the LDH, which is due to the absence of the calcium from the brucite type layer, and also from the bidentate configuration of the carbonate anions. Also, we can observe that in the spectrum of the phytoextract, the characteristic stretching vibration of the OH and the CH aromatic CH groups. And in the case of the spectra of the simple hydrogels, we can observe the characteristic peaks of PEGDA. No? Okay. the characteristic peaks of PEGDA, which is CH2, COC, OH, or C-double-O bonds. Also, the asymmetric stretching vibration of the C-double-C bond from the acrylic bond of PEGDA. Also, we can observe that the intercalation of the LDH inside the hydrogel maintain the same characteristic bands of the hydrogels, but their intensity depends on the quantity of the LDH inside the hydrogels. So, in conclusion of the FTIR results, we can say that no non-covalent bonds take place during the encapsulation of the phytoextract inside the LDH and also inside the hydrogel. The same results present homogeneous morphology for the obtained composite hydrogels. We can observe that the hydrogel present smooth and compact morphology with the LDH dispersed very good. We can observe also cracks obtained during the lyophilization process, which leads to a formation of porosity. Also, we can observe in the case of the hydrogels with intercalated LDH with phytoextract that the surface presents some elongated pores and interconnected channels. Also, we can observe in the cross-section same images that the hydrogels which contain LDH with Ramulus frangula, the LDH is better dispersed in the polymeric matrix compared to the one with just the simple ADH. The equilibrium swelling degrees and the rheological behavior. So the equilibrium swelling degrees increase, the swelling ratio increase with the addition of the LDH. With the increasing of the LDH, we can observe also an increase in the swelling degree and also an increase with the addition of the phytoextract inside the LDH. Also, we can observe that the hydrogels were also, we can observe that in the case of the hydrogels, which consist in which contains the LDH, which has magnesium, calcium, aluminum, or iron, and the one contains with magnesium, calcium, and aluminum, that the swelling degree is a little bit lower compared to the one with just magnesium and iron. This fact is due to the it's deteriorated due to the number of compounds inside. There are 2 compounds inside the LDH, and that block the swelling degree, the increasing of the swelling degree. Okay, so the rheological properties, we can observe that the mechanical properties is enhanced, in this case due to the LDH intercalated layer inside the polymeric chain of the hydrogel. And also we can observe that the elastic modulus is slightly higher than the loss modulus. Fact that can be attributed to also to imperfection of the material of the hydrogel. Also, the control release experiments, we can observe that the phytoextract is released slower in time in the case of the phytoextract inside the LDH. And also we have also a more slower release In the case of the hydrogel with the LDH and the phytoextract, this can be deteriorated due to the fact that there are some interaction between the LDH and the pegda chain and the ramus frangula molecules. So we can also observe that with the increase of the LDH inside the hydrogels, there are a decrease in the phytoextract release. But also we can observe that the release of the phytoextract depends very much on the type of the LDH used. So in conclusion, this study proved the non-covalent nature of the interaction between the phytoextract components LDH and the hydrogel. The surface composite of composite hydrogel with incorporated LDH exhibit a less homogeneous and more agglomeratic structure than the sample with the phytoextract. The equilibrium swelling degrees of the composite hydrogel increase in the presence of the LDH and the LDH with the phytoextract in the gel network, and also the study present an efficient slow release at the intestine pH for slow intestinal transit treatment. For the further studies, there are foreseen the studies on the interaction between the components of the system, on the element content, and on the stability at different temperature and pH, biocompatibility, and animal studies. Thank you for your attention. Oh, sorry.
Thank you very much, and congratulations for your work. Please, if you have questions, please.
Okay.
So what does it mean, hydrogel imperfection?
Hydrogel imperfection, they're referring the small holes that is obtained in
because hydrogels are by definition microscopically heterogeneous. So there are always maybe what you call imperfections. So that by definition, we have a macroscopically homogeneous, but microscopically with a different cross-linking density. So you have probably, this is what you call imperfections. I don't know.
Yes.
Okay. And the comment, you have a very good results of controlled release. In fact, in your case, you have controlled release because it seems that there is a linear relationship between the kinetics and or the amount of the drug that is released and the time. And this means that you have a zero order kinetics. And that is the Saint Graal of the pharmaceutics. So I think that you should go forward and to go further in this because it seems that the matrix gives a zero order release, and this is excellent. In fact.
Okay, thank you.
Thank you. If there are some other questions, or from online, if there are questions. Thank you very much.
Thank you.